This pictogram shows the collapsed beginnings and ends of every human intron. The height of each letter reflects how commonly this nucleotide appears at this position among all human splice sites. The conserved GT and AG are essential for intron splicing, and if disrupted by a variant, are known to alter splicing. However, the spliceosome binds a wider region with greater sequence diversity, so it's hard to know if a splice region variant will alter splicing or not. A barrier for clinical workforces has been a lack of an empirical feature that discerns a strong splice site from a weak one or an unusable one. We have addressed this problem with NIF, or native frequency. NIF represents the variety of human splice site sequence combinations that are known to allow splicing to occur. NIF divides each splicing motif into positionally anchored, overlapping sequence windows of 9 nucleotides, and measures how commonly this sequence occurs at this position of the exon-intron junction among all known splice sites of the same class. Let's look at the PKD1 intron 13 donor. Here are the 4 sequence windows. The most intronic window, where U6 binds, is found in 317 other introns. The 2 central windows, where U1 binds, in 601 and 592 introns. And the most exonic window, where U5 binds, is found in 172 different introns. NIF tells you that these sequences splice efficiently at hundreds of different introns. To make it easy for clinical teams to gauge how common splice site sequence windows are before and after a variant, we've optimized a 0 to 1 NIF percentile scale. Let me explain how this works. The least common 9 nucleotide sequence has a NIF of 1, meaning it's found at only 1 human intron. All 3,700 introns with a unique donor sequence form the first and second percentiles of the NIF scale, the most rare. The most common 9 nucleotide sequence occurs at nearly 3,000 introns and alone forms the 100th percentile of the NIF scale, the most common. All other sequences fall somewhere between these two extremes on a 0 to 1 most to least common scale. NIF works on the logic that common motif sequences are strong because they've been fine-tuned through evolution to be used efficiently by the spliceosome, while very rare or unique motif sequences are weak because they've evolved to require splicing enhancers to help execute the splicing reactions for gene regulation. So going back to the PKD1 intron 13 donor, the GENEie NIF table shows both the raw frequencies and the NIF percentile scores, so users can easily see that in terms of how common donor sequences can get, this PKD1 intron 13 donor is about average. Splicing fails when the spliceosome can't recognize or use a splice site. We use 3 windows of NIF equals 0, a sequence combination that does not exist at this position of any human splice site, to define a non-existent and unusable splice site, because this is the mathematical feature that defines 96% of essential splice site variants. The critical discovery was determining that many pathogenic extended splice site variants also create a non-existent splice site, and when this happens, missplicing odds are more than 1,000 to 1. If a variant creates a non-existent splice site even with a GT or AG in the correct position, it's statistically very unlikely to work. NIF makes it easy to see that this +4 variant at the same PKD1 donor creates a very rare donor, giving 100 to 1 missplicing odds, whereas this +3 variant makes a more common donor sequence with 100 to 1 splice neutral odds. Our statistics prove that these rules of splicing logic hold true for 40,000 canonical splice site variants and 10,000 cryptic splice site variants. While splicing enhancers and repressors are doubtlessly important, compelling evidence shows NIF accurately measures the intrinsic strength of a splice site, making interpretation of splice region variants easier.